Hello friends, welcome to the new class. In this class we will study the time response of a second order control system. In general, a second order control system can be expressed as T of S, where T of S is your transfer function of second order control system, is given by output divided by input and is equals to omega n square divided by s square plus 2 zeta omega n s plus omega n square, where this second order control system is specified by the highest power of s in the denominator as 2. Okay, where this term is known as zeta and it's actually a Greek letter, okay, pronounced as zeta, and this is known as damping ratio, and omega n is equal to the natural frequency. Okay, if we express this second order control system as a block diagram representation, then in block diagram representation this can be represented like this, that we have to set a forward path transfer function omega n square divided by s times s plus 2 zeta omega n with Cs as the output. This is your summing box. Here Rs is the input with plus sign and a unity feedback. Okay, so in this way this becomes your signal ES. Now let's see the time response of a second order control system subjected to unit step input. So in this case, your Cs is equals to R of S multiply omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay, so if Rs is equals to unit step, then this will be equal to 1 by s. So substitute this equation in equation number 1. We will get C of s is equals to 1 by s multiply omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay. Now completing the square, this square term, then we can write this square term as one by s multiply omega n square divided by s plus zeta omega n square plus omega n square under root of 1 minus zeta square. Okay, now separating into partial fractions. So we get C of s will be equal to 1 by s minus s plus 2 zeta omega n divided by s plus zeta omega n square plus omega n square multiply 1 minus zeta square. Okay, now let omega d is equal to omega n under root of 1 minus zeta square, where omega d is known as damped frequency of oscillation. Okay, please be remember this factor. So we get C of s will be equal to 1 by s minus s plus 2 zeta omega n divided by s plus zeta omega n square plus omega d square. Okay, now separating it, that is 1 by s minus s plus zeta omega n divided by s plus zeta omega n whole square plus omega d square minus zeta omega n divided by s plus zeta omega n square plus omega d square. Okay, so if we multiply this term with omega d square, omega d and divided it by omega d, then it looks like this. That is 1 minus s, 1 by s plus zeta omega n s plus zeta omega n whole square plus omega d square minus zeta omega n by omega d multiply omega d divided by s plus zeta omega n whole square. Okay, so this term will now converted into a Laplace transform of cos theta. Okay, and this term converts into the Laplace transform of your sin theta with a factor, exponential factor, that is zeta omega n. So we can write this as by taking Laplace inverse transform of both sides. We have C of t. For this function we get 1 for this function, because there is a plus factor with s, so we have to multiply e raised to power minus zeta omega n t cos of omega d t minus zeta omega n by omega d multiply e raised to power minus zeta omega n t multiply sine of omega dt. Okay, now since omega d is equals to omega n multiply 1 minus zeta square. Okay, so rewriting the above equation, that is Ct is equals to 1 minus e raised to power minus zeta omega n t cos of omega dt minus zeta omega n divided by omega n into under root 1 minus zeta square into sine of omega dt. This omega n cancelled with this omega n, so we will get 1 minus e raised to power minus zeta omega n t divided by taking 1 minus zeta square under root common, so that it will get multiplied with this term, this cos of omega dt minus zeta times sine of omega dt. Okay, now put sine of phi is equals to under root 1 minus zeta square, so this will gives you cos of phi is equals to zeta. Please be remember these two factors. Okay, so we get C of t is equals to 1 minus e raised to power minus zeta omega n t divided by under root 1 minus zeta square multiply sine of phi cos of omega dt minus, taking minus as common actually, so this will, we have taken minus as common, so this should be plus here, this should be plus here. Okay, so we will get cos of phi sine of omega dt. So using the trigonometric formula, that is sine a plus b is equals to sine a cos b plus cos a sine b. So we will get the final result as e raised to power 1 minus e raised to power minus zeta omega nt divided by under root 1 minus zeta square multiply sine of omega dt plus phi. Okay, so we get the final response of second order control system when subjected to a step input as this one, where this phi is equals to tangent inverse under root of 1 minus zeta square divided by zeta. This is because from this equation and this equation we can easily get this response. Okay, if we closely examine the response of second order control system, then we will find that it consists of a sinusoidal response which is exponentially decaying. Okay, and the exponential decay with a time constant, here you can easily calculate its time constant from this term, that is like this, that is time constant of this function will be equal to one by zeta omega n. Okay, if we draw its response, then it looks like this. Suppose this is the axis and here we draw the input. Let us suppose this is your unit step input. Okay, this is your time axis, 0 here, and this is your C of t. Then as the output, this output consists of a term sine function with exponentially decaying sine function, and this is to be subtracted from 1, so it should be started from 0 here. like this. Okay. So in this way, this nature occurs due to the time constant. This is your time constant T is equals to 1 by zeta omega n. Now if we increase the time constant, then your settling time, which may occur previously at this position, suppose this is your 0.02 units, then due to the increase in the settling time, the response may look like this. Okay, this is another T. Suppose it is your T1. Okay, where T1 is greater than T. Okay. Now we will see that the time response of control system consists of zeta here and omega here. So it depends on the value of zeta as well, where zeta is actually your damping ratio.